Alright guys, well I'm glad that you guys could make it, and it's greetings to everybody that's hopefully at least watching this online. We do have 15 enrolled in this class, and it's past the drop deadline, so yeah, we're crossing our fingers that you're all following along. And yeah, so anyway, so kind of like what Adrian talked about on Monday, I'd say this week is our first week of really doing the differential part of differential geometry, now that we've gotten the formal aspects out of the way of defining a surface, figuring out what is okay and what isn't, and so on. Now we can start to do the kind of math that we're really interested in. And probably the very first quantity that people tend to associate with differential geometry, if you've ever seen it in the math department or even really tried to think about what this topic probably involves, is understanding and computing the curvature of a surface. So on Monday, we talked about how you would compute curvature on a continuous, smooth-looking surface. And today, we're going to have our dual lecture on how to compute curvature on a discrete surface built out of triangles. So before we get started, I thought I'd better review a little bit on Monday. And being the horrible mathematician that I am, instead of having nice notation and going through all of the formalities of curvature, I thought I'd draw lots of pictures and kind of have the pictorial view of what's going on in some of Monday's lecture. So anyway, for our purposes, we're going to have a surface, and we're going to call it S. There's S. And there are a couple things we need to know about S. Well, for one thing, when we're on S, we might stand at a point, and we'll label a point P, P's point. And the surface has a normal end. And we went through how you can compute the normal end for a smooth surface on Monday, but it's pretty simple, right? The normal is this thing that points perpendicular to the surface at every point, right? It's just a vector. And perpendicular to the normal is this thing called the tangent plane, which I've drawn in this little rectangle here. Hopefully you're all with me so far. So the first thing that we did is we defined this thing called a Gauss map. Right? We did the same thing, we followed the same story when we talked about curves. Remember, we talked about curvature, and we talked about the way that one way to define curvature for a curve, at least on the plane, is to write this map from your curve to the unit circle that just gives at every point on your curve the normal. Yeah? So now the sort of two-dimensional analog of that animal is the Gauss map for a surface, which is a map, and this is where the choice of the letter S probably is a little bit unfortunate. It's a map from the surface S, right, this bent thing here, to the unit sphere S2, right? And all it does is says that at this point here, P, you know, the surface has some normal on the unit sphere. Right? So when we measure curvature, effectively what we're measuring is how this n is sliding around the unit sphere as we walk along the surface. Yeah? And so what we can do is things like draw curves, and we usually call curves gamma. Notice I'm kind of introducing a notation, because if I forget later on to always say gamma the curve, whenever you see this letter, I'll try to use it for a curve. We can trace curves and look at how the normal varies and so on. And in fact, that's exactly how we measured the curvature of a curve back in week 2. Yeah? So now kind of continuing our story from Monday in a very compact way, what did we do? Well, we have this function n, right, this Gauss map, that takes every point on a surface and maps it to a point in the unit sphere just by computing the normal, and we can differentiate this object, right? So what does the derivative look like? Now my notation actually lies a little bit, but we'll come back to that in a second. But in particular, right, if you take the first derivative of something, you've got to tell me what direction I'm taking the derivative in. Right? So if I'm standing at point P, what you're going to do is we're going to play a game where you give me a direction from my feet, that's the direction I'm going to walk in, and I'm going to give you the derivative of the unit normal to the surface in that direction. So the direction that I walk in, that I'm going to be differentiating, is the tangent plane at P, right? So that's P of S. And what I'm going to give back to you is the derivative of the unit normal, which is actually not in the unit, the tangent plane necessarily. This was a mistake on my part. But usually we think of the derivative of dn as you take the derivative of the normal, right, in this tangent direction here. And we talked about how to do that last time. And then we really only care about the part that we project back down onto the tangent plane, which is why I wrote this here, but I kind of skipped a step. Anyway, so this derivative thing we can think of in any number of ways. Those of us that are engineers probably think of this as sort of a 2x2 or a 3x3 matrix, depending on what space we're in, and alternatively, this is some operator from tangent space to tangent space, whatever. But when we define the second fundamental form of a surface, which I wrote here a sub p, I think actually the letters might have changed for Monday's lecture.
I use it.
You use it? Oh, cool. All right, so what we're going to do now is we're going to take two tangent vectors to our surface. Well, they're v and w. And what we're going to say is that one way to express this derivative dn is to say I'm going to take the derivative dn in the direction v, right? And then remember that I told you I only really care about the components of the derivative that are tangent to the surface. So what am I going to do? Well, I restricted w to be a tangent vector to my surface, and I have this operator that takes v and w and gives me back the inner product of the derivative of n in the v direction with the tangent vector w. So notice that if I fix v and kind of vary w around, that's enough to recover dn, at least in tangent space. Yeah? So I haven't lost any information. This is just a very slick way of writing down derivatives of the normal on the surface. And finally, we get to kind of the end of the lecture on Monday. And then we define these objects called principal directions and principal curvatures. So remember, we have this second fundamental form. And what it tells me, yet again, is I stand at a point P, I look in direction V, and I want to find now in some other direction W the amount of the normal derivative in the V direction projected onto this other tangent vector. Yeah, a lot of words. So to kind of clean things up a little bit, we can look at this operator A, this second fundamental form, and extract some interesting information from that. Now, the first thing that you might ask is, let's say that I put in V twice, right? So I have the second fundamental form, and now I take a tangent vector, and I say, I differentiate, the normal in the tangent direction, and I'm going to take the dot product of the derivative of the normal with the direction that I'm already walking in. Does that make sense? This sort of parallels our story for when we were talking about how to define curvature. Do you remember when we talked about the Fermat frame? Right? Well, what happened when you took the derivative of the normal vector on the Fermat frame, right, and then you took the dot product of that with the tangent vector, hopefully you get curvature back out. Right, torsion? No, I think it's curvature. and exactly the same story is happening here. So in particular, if I take the same tangent direction, I put them in twice, I'm going to get a number that I'll call the curvature of my surface in the direction that I'm pointing in. Yeah? And one thing I might do is actually parameterize these sort of tangent plane directions by choosing some canonical direction and then measuring every way that I can point from there just as some angle theta from the initial place that I'm pointing. Yeah? And a convenient direction that I might choose for the direction that I'm pointing in. By the way, we're only going to use unit vectors for v and w, and that's why I think about this as kind of tracing out a circle. Right? So probably the easiest sort of canonical direction I might choose would be the direction where curvature is, say, biggest. Right? And we'll call that direction the first, or the largest principal direction at P for your curvature. Right? And now what I believe, well, probably Gauss proved, I don't know. Although I think it's what, Euler's theorem? I forget the name. One thing you can look at, just because of the eigenstructure of the second fundamental form, is if you know the biggest curvature, we'll call him K1, and you know the smallest curvature, and we'll call that K2, then a couple nice things happen. First of all, they occur in perpendicular directions. These are called the principal directions for the surface. And we can parameterize the curvature as I kind of, walk around standing at P and stare in all these different directions theta, using a very simple function. And you notice that this looks quite similar to when you look at how a 2x2 matrix deforms an ellipse, and that's because that's exactly what's going on here. So anyway, to make a short story long, basically the big story of curvature on a two-dimensional surface, it involves you stand at a point P, you take the derivative of the normal in all the different directions that you can point in, and then you notice that it's enough to only know the minimum and the maximum curvature in directions that I'm standing at. So hopefully does this story make some sense so far? Because if it doesn't, the rest of the lecture is not going to be comprehensible. Oh, got a nod. Cool. All right. So, who cares? Well, one reason to care is that sort of similar. Remember, we had this big theorem called the fundamental theorem of what was it? Curvature of plane curves and this and that and the other thing. Basically, what it told us is that if we knew the curvature of a curve, then up to some range of motion, you could actually reconstruct that curve. Yeah? So it turns out that we can prove a pretty similar theorem under certain conditions for surfaces as well. That is, if we know all of the principal curvatures and directions, then we can reconstruct the surface itself. I don't think we'll go into the proof of that in this class because it's a little bit hairy. But there are other reasons to care about curvature that are somewhat more practical. So first of all, if I know something about the curvature at every point of a mesh, then I know something about the geometry of a point. So remember, we had these principal directions, principal curvatures, right? They're the max and the min curvatures. And then from them, we derived two other curvatures, right? And what were they? Well, the first one, I guess I've flipped the order here, but probably the most important, or the one that we think about the most, is this Gaussian curvature, where you just took K1 and K2 and you multiplied them together. Now, what does this do? Well, if the Gaussian curvature is a product of kappa 1 and kappa 2, then when is it positive? Well, it's positive when kappa 1 and kappa 2 both have the same sign. And it's negative when they have opposite signs. But what does that tell us about the surface? Well, if the curvature has the same sign in all directions, then my surface locally looks like a bowl. It's sort of concave or convex. And if the curvature has opposite signs, then what it's saying is that in one direction, at very least, in one of the two principal directions, the surface is curving up. And in the other of the two principal curvature directions, the surface is curving down. Right? So your surface has this sort of saddle shape. Yeah? So if we compute Gaussian curvature on our favorite dragon model here, what happens is that the Gaussian curvature picks out all of its little scales as being these little convex pieces. Right? And then in between the scales, right, when you're transitioning from one scale of the dragon to the next, you have this kind of funny little hyperbolic piece where it transitions along. And you can see that in the red. I think here we just see the sign of curvature, either positive or negative. And that's why you have this little red and blue pattern. Now, if we multiply the two curvatures to get Gaussian curvature, I gotta give you a second number if I want to have a hope of being able to recover kappa 1 and kappa 2 and not losing any information. And one other one, although it's not the only other derived curvature. In fact, there's this book by a gentleman whose last name is Coendering, I can never pronounce that properly, who defines a whole slew of different functions of kappa 1 and kappa 2 and tells you how they have to do with geometry of surface. But usually the other one that we think about is the mean curvature, and that's just the average of kappa 1 and kappa 2. Yeah? So the mean curvature has lots of bizarre properties. For one thing, it doesn't really care if your surface is hyperbolic or parabolic. Yeah, so it's not something that we're measuring anymore. But instead, it sort of measures, you can think of it as the disparity between the max and min curvature in some sense. Right? If my surface is really far bent up in one direction and really far bent down in the other direction, the mean curvature is still 0 because one's bent up and one's bent down. And we'll return to some other interpretations of mean curvature when we talk about bending of a surface and how do you measure, for example, when you have a piece of cloth, right? The piece of cloth, or at least a piece of paper, if you look at its Gaussian curvature, is always 0. Paper is something called a developable surface, which means that it has exactly 0 curvature. In fact, one way to think about that is you take your favorite sheet of paper and you try and bend it, you'll always see these sort of ruling directions that are flat. And those directions are directions of 0 curvature, and no matter how hard you try, any number you multiply by 0 is still 0. The mean curvature of a sheet of paper depends on what way you bent this thing. And we'll notice that when we're simulating cloth and doing other things that involve sort of understanding how a surface is bending, mean curvature is going to play a big role. And the cool thing is that now that we've gotten sort of our basics of differential geometry down, we're going to start to be able to talk about these sorts of applications. What are some other things that we can do with curvature? Well, as I mentioned before, if I know the fundamental forms of the surface, I can go back to the geometry of the surface itself. In fact, one pipeline for editing a surface, or smoothing, might be that I compute all these curvatures, and then I do some operation on them, like I smooth them out, or I exaggerate them in some way, and then I go back and reconstruct the surface from the modified curvatures that I have. This turns out to be a difficult problem. The sort of compatibility conditions for making curvatures integrate back to a surface are not necessarily that nice, but it is something that people have done. Another thing we can do is use curvature as some measure of the fairness or the smoothness of the surface. Right? So what do we know about curvature? Is it's completely based on looking at my feet. I don't have to look anywhere on the surface other than right underneath my toes to measure the curvature of the surface. So let's say that I have a really noisy surface. This model is another, in the pantheon of geometry models. This one's name is fan disk, and he also appears a lot. But let's say that I'm standing on the fan disk and I'm looking at my feet on this very noisy guy. Well, locally, the surface is jumping up and down, right? So it has tons of curvature from point to point to point to point, yeah? Because at every single vertex, the surface is changing the way that it's pointing, it's moving up and down, along the normal direction, and so on. Whereas if I have a smoothed out fan disk, like the guy in the bottom left here, right, he has very low curvature. In fact, it's probably pretty much zero on these flat pieces. So one very reasonable objective for smoothing out a surface, say, would be to simply try to minimize its curvature subject to the surface being some approximation of where you started. Cool. And that's not the end of our story. In fact, one application that you might have seen last quarter was that curvature could be used to find interesting features on a surface. So this is one of many papers whose step number 0 is you take in a surface, and before I render it, I'm going to compute principal curvatures and directions along the whole darn thing. Right? And these directions tell me something about the structure of the surface locally. In fact, one thing I could do would be to trace out something called the principal curve. Right? A principal curve is nothing more than just walking along the principal direction from point to point. And these sorts of curves give me some idea of sort of the main ridges and valleys and so on the surface. And so there are rendering techniques that say, okay, rather than simulating light bouncing around, maybe what I really care about is showing a surface in such a way that I highlight the primary geometric features. Right? This sort of imitates the way I might draw a surface with a pen. Right? Well, if I'm doing that, I have to have some geometric way of finding the interesting features, and curvatures are oftentimes a good starting point. Alright, and finally, one other application you might have is for remeshing a surface. So a lot of times, for example, in finite elements and simulation, or in certain architectural applications and so on, we care a lot about the underlying mesh that we're going to use to represent a surface. And there are lots of different objectives you might have. For example, maybe you want your mesh to have nicely shaped triangles. Maybe you want your mesh, as in this figure, to really be constructed out of quads instead of triangles, right? This is something we probably won't get into a whole lot in this class. And this is a really hairy problem. How do you take a triangulated surface on the guy, like the guy on the left, and make him into a good approximation of the original surface, but with triangles or quads or whatever you like that satisfy whatever property you're looking for? Why is this such a hard problem? Well, you have to simultaneously make two decisions, right? First, you have to decide sort of what direction you want all of these little pieces to be aligned with, right? And the second is a sort of scary combinatorial question, right? Which is, this guy is constructed out of quads, he's constructed out of triangles, so it's not enough to just do local operations where I just walk around these triangles and like push vertices around, kind of like what we like to do in differential geometry. You have to actually change the topology of the mesh. But anyway, that aside, if I'm trying to decide sort of nice directions to align the geometry, these quads and these triangles and so on, one sort of popular choice for how you might guide this type of meshing would be the first thing you do is compute these principal direction fields. Right? Here's the minimum curvature direction. You can see it kind of points up the thumbs, and then here's the maximum curvature direction, right? And it's going to point around the thumbs of this hand model. You guys see why this makes sense, right? The most flat direction along this thumb is going to be right up along the side. The most curvy direction of the thumb is going to be right around the radius, yeah? And then once we have those, we can start to trace out curves and use those to guide our remeshing scheme, right? And this is one of many papers that uses an approach that's somewhat similar to this. By the way, it's kind of a fun topic for me. As I was preparing this lecture, I remembered that I had a funny high school job like 12 years ago that involved actually implementing a lot of these very papers. I found them on my old hard drive. It's kind of funny. And apparently we actually have a patent on Gaussian curvature, which should not exist. But anyway. So I thought I'd start today with a paper that might be familiar to some students from last quarter, and it's sort of the standard citation for computing curvature, even though it turns out that nobody uses this in practice. So we'll start with how we compute this curvature using Tobin's method, and then all of the reasons why we need to improve it in a lot of different ways. By the way, this was a paper from ICCV, right, a computer vision conference, all the way back in 1995. Right, so we've thought that computing curvatures is important for a very long time, at least in the, the time scale of differential geometry on computers. So what does Tobin do? Well, let's start on a theoretical smooth surface before we discretize anything. And let's say that we're standing in point P, as we like to do in this class. And we look at a curvature, or rather a tangent direction T, right? And remember that we can parameterize our unit tangents at point P by just measuring an angle from some canonical starting point, and then kind of walking in a circle. Right? Well, this thing is nothing more than just some vector in free space. Right? And the curvature kappa is just, remember we were going to define it as sort of the curvature of the curve through my feet, projected back down onto the tangent of the surface. And I can define this funky matrix, which is what Tobin defines, and also is something that we use in differential geometry sometimes, where you take the outer product of T in itself. Notice that T is 3 by 1, right? So what is this product here? It's 3 by 1 times 1 by 3. Yeah, so this is 3 by 3 matrix here. Or 2 by 2 if you think of yourself in tangent space, doesn't really matter. And what I can do is take this 3 by 3 matrix and multiply it by the curvature in that direction, and then just integrate this function, just element-wise, right? So you're really doing 9 integrals between minus pi and pi. That is, I look at my feet at point P, I compute the curvature in this direction, I compute this little matrix, and now I'm just going to do the hokey pokey and turn myself around and integrate this function all the way around the loop. Yeah? And by the way, we know how to compute tangent directions, we know how to compute curvature, no big deal. Yeah? Of course, if we already knew kappa 1 and kappa 2, this algorithm wouldn't be very useful. So we're going to go kind of in the reverse direction in a minute. So one thing that you guys should prove to yourselves at home, because we're grown-ups in this class, is that this matrix M has a couple of useful properties. Well, first of all, his eigenvectors are the normal vector and the two principal curvature directions. Now this one's really easy to prove, right? Because what's going to happen when I multiply this by n? Well, I can kind of move the n inside of this integral, and then you'll notice that you'll have t theta transpose times n, right? T theta is a tangent vector, n is a normal. And a vector transpose times another vector is nothing more than their dot product. And the dot product of a tangent and a normal is what? Guys? 0, yeah. Again, I guess it was pointed out to me that not all of my questions are answered by 0, but this particular one is. So anyway, so what this tells us is that if we know this matrix M somehow, that I can go backward from n to the two principal directions, and in fact there's this kind of magical formula involving eighths that gives me the curvatures based on the eigenvalues of this matrix. In fact, if somebody can tell me like an intuitive reason why that h should be there, I will give you extra credit because I can't like get a good intuitive grasp of how it gets there. It's like this. It's like a funny byproduct of trigonometric integrals. So anyway, all Tobin does is says, okay, I'm going to find a way to approximate this matrix M. So let's say that I'm standing at a vertex of a triangle mesh now. One thing I can do, if I'm just standing at vertex I, and I look toward one of my neighbors, which we'll call vertex J, is I can come up with kind of a corny approximation of the curvature in that direction. Right? How can I do that? Well, I have the normal to my surface at vertex I, I have the normal at vertex J. Yeah? I can subtract them, divide by the length of that edge, and that's some idea of the derivative of the normal of the surface. Right? So what does Tobin do? Well, he says, okay, I'm just going to iterate over all of my neighbors at a given vertex, and I can compute the tangent direction just as the difference between the positions of these two vertices. I can compute the derivative of the normal by just subtracting these things, and then I'm going to come up with some reasonable weighting scheme to just combine these objects in a similar way to this this outer product here, or this integral. Yeah?
A picture might help.
Oh, sure. I should have drawn one on the slides, but I didn't. Alright, so let's say my Frederick contact gives me a hard time because whenever I give examples, I get things like, okay, that's 5, and that's uncommon, undefined. Anyway. Yeah. I guess we can fix this easily. There we go. Okay. So basically, I'm at vertex I. Here's vertex J. Right? So remember that it's easy enough, in fact we covered this I think in the last lecture, to compute some approximation of the normal at vertex I, the normal at vertex J. Right? So to find some approximation of the derivative of the normal, well, all I'm going to do is put a big minus sign in front of these things. Right? And that's sort of the derivative of normal along this edge, just solve the first order. And if I divide by length L, then I get the actual derivative of the normal in that direction. And then all Tobin does is sort of sum all these guys up with a particular choice of weights. So what does he do? Well, he says, okay, let's say, now I have a nicer picture. Let's say I'm at vertex I and vertex J. Then we're going to make the weight for the edge between these two guys proportional to the sum of the areas that are adjacent to that edge. Right, so the area of triangle 1 and the area of triangle 2. It's just some model, some reasonable way to count influence. He's not too worried about convergence and all these things. So anyway, yeah, and the curvature is self-divided difference approximation. So now we have some way to compute this matrix M, right? In fact, he's sort of overdetermined in the sense that the things typically have valence 6, but M is a 3 by 3 matrix, right? And so there's some amount of error tolerance that's built in here. And then I extract the eigenstuff and out comes principal directions. That's the beginning and end of this algorithm. Very fast, right? Especially if my mesh is stored as a half edge, right? Then this algorithm looks just like the algorithms we talked about in my last lecture, where remember we had this half edge, you want to iterate over the neighbors, so you kind of flip and follow tails and all these games. This is a primary example of when this is useful. So we got a problem, which is which we've illustrated here. So somebody who published a paper, of course, you know, providing a much better solution than Tobin's paper, provided a good example of when this algorithm doesn't work. So let's say that I have a triangle mesh and it's really noisy locally, right? I've got all these little triangles that are bending in and out and so on. Right? Now Tobin's algorithm, what is the very first thing that he does? Well, he takes the normal vectors of the surface and just looks at the one ring of a given vertex and looks nowhere beyond that to compute this curvature. And in fact, there's also one more fishy question, which is that we're differentiating these normal vectors n, right? But how did I compute them? Well, if you've taken CS, 248, 148, some graphics class, then you know that sort of reasonable schemes for finding normals to a surface involve you take normals to triangles, which are kind of obvious, right? They're just flat, and you average them in some way. Right, so if my surface is really messy, then I've got all kinds of sources of messiness that all get combined in a not nice way. Right, I have noisy normals, and then I'm going to differentiate these noisy objects to get an even noisier curvature. And you can see that here. So here's this little kind of zoomed in piece of a noisy surface. And in general, or you can see the surface is kind of curved this way, and the principal directions you extract using this algorithm kind of follow the geometry this way. But locally, you get these curvatures that every once in a while will point somewhere you don't expect. Like here's one that points up. And why the heck should this direction point up? Well, the other one's pointing to the right. And it's just because you have these very localized little issues with the triangles that aren't so great. So in reality, basically what I wanted to start, with this, yeah?
Is it a reasonable preprocessing step
To smooth your mesh, you have to be very careful. Because how do we smooth a mesh? Well, oftentimes the way we smooth mesh is by asking that the curvature decrease. So you have a ticketed egg problem. There are schemes that don't do this, but they're often very expensive. So Tobin's algorithm is one of many examples that we'll cover today. Well, at least two, I think, depending on time. That sort of are the name of the game in a lot of these curvature computation papers. By the way, if you have your laptop and you just like open up Google and you Google for like principal direction on triangle mesh approximation, you'll notice that there are like journals and journals and journals worth of papers on this topic. This is one that's very important for people and a very difficult problem because remember, curvature is a second derivative. So if your surface is already kind of noisy, taking this second derivative of a noisy function is like a really difficult problem. But in general, our game, to kind of steal something from South Park here, is that in our first step one here, we're going to collect some local data about my surface, right? So in case of Tobin's algorithm, we have our vertex positions and our normals. Step 2, we'll do some magic that usually involves one of our favorite formulas from differential geometry. There's a whole library of them. And step 3 is we'll have our curvatures just come out. And now, at this point, I should give you guys a big warning, which is that this stuff, these papers generally are engineering disguised math. Right? We're going to write all of our curvature computation methods in this very beautiful differential geometric language. And then in section 5 of our paper, we will have discretization. And that's going to be where all these really yucky approximations take place that take us from beautiful math to engineering. Right? And it's really important to remember that, because there are all kinds of theorems that we'll talk about involving curvature and integrating curvature, adding together and differentiating it and so on. And these theorems, in general, unless we design our computation method to hold them, in general, they'll only hold approximately. In fact, really what somebody should do is write down a battery of tests and sort of pieces of information that we know should be true for curvature, and just run all these 50 bajillion algorithms through them and see how much they hold. Because I have a feeling a lot of them are quite far off from what we expect. Turns out that it's very easy to draw a vector field on a surface that kind of looks like it curves around bendy parts, but it's very difficult to verify that it's actually the curvature of that surface. So anyway, probably the main takeaway that I'm going to want you to get from our lecture today is that you should use your application to motivate your choice of curvature. Notice this is a phrase that we do not use in theoretical differential geometry, which is choice of curvature. Right? In differential geometry, there is curvature. So this is going to be, again, this is where our engineering comes in. And there are all kinds of applications we'll have in mind. Things like simulation, like what Trent asked about, there's smoothing, analysis, meshing. For example, non-photorealistic rendering is a really interesting example that we won't cover today. Because in this one, what you really care about is that your curvatures are stable. Right? I don't really care if these things are mathematically the physical curvatures. This is just some rendering technique anyway. And chances are your favorite cartoon viewer isn't going to notice if, like, shoot, these curvatures are off. But they will notice if your curvatures are like buzzing from frame to frame of your video. So that's an example where it's kind of excusable if your curvatures are not very accurate. So, sort of going down the pantheon of curvature papers that people generally cite, the next one on the long timeline was written in 2004, so about a decade after Tobin's paper, and it's by Rosinkowitz, hopefully I said better, Simon. And this is another sort of standard method of computing curvature, and in this case, actually, his motivation was to compute curvature for these rendering methods. And you can see he has an example of a little hair here. So for him, what he was really worried about was a very stable measure of curvature that isn't going to be very locally noisy to make it difficult to trace these nice curves on the surface. So I decided, we have to make a decision at the beginning of a lecture like this, which is all of these papers use their favorite differential geometry book, and each book uses completely different notation. And you decide whether you're going to translate them all back to the notation for your class or keep it in the notation of the paper. I thought since we're kind of having a high-level view, it's actually better to keep it in their notation so you can connect between what I'm going to talk about and when you actually look at this paper. That was my decision. I apologize if you don't like it.
But yeah. Just to say, this does coincide with our definition, happily.
Oh yes, this one is fine. In fact, did we use this Roman numeral 2?
We didn't use 2, we used A for that.
Yeah, we used A, but if we use this as A, then it's basically the same. And this Roman numeral 2 shows up, especially in sort of old school math books, I think. 2 for second fundamental form. Second. Right? Can anybody guess what the first fundamental form looks like? If anybody says 0, I swear. Yes, it's a Roman numeral 1. Anyway. So one way to think about the second fundamental form, if we're engineers, remember mathematicians, we like to think of it as this operator, but as engineers, we can think of it as a matrix, right? One way to do that would be, let's say that I parameterize my surface with u and v directions, right? So I'm just going to locally slice these little curves on my surface that are sort of u and v parameter directions. Remember that Adrian proved a couple weeks ago that you can always do this locally on a surface. In fact, we're going to ask that u and v be perpendicular. At least at the point that we're interested in, which turns out you can also do. So anyway, the second fundamental form matrix is nothing more than I take the derivative of the normal in the u direction, that's first column. Second derivative column is I take the derivative of the normal in the second direction. Reasonable enough. So in particular, we can write this as a 2 by 2 matrix because we only care about the derivative of the normal projected back down to the tangent plane. Right? This is something that will keep coming back up. So how can I do that? Well, I take dn du And I can just take that in the dot product with u, right? So I think the first row here is sort of the u component of the derivative. The second row is the v component. Yeah? So this is just some expression of the second fundamental form. This makes sense? Cool. Yeah, I'm going to assume that these guys are orthogonal. So it's actually don't see that. So let's say that I choose some direction s. There should probably be a vector over s. I apologize. And s is going to be some combination of the two tangent directions u and v. Yeah? The coefficients c1 and c2. Then, if I want the derivative of the normal vector of the surface in the s direction, what do? Well, all I do is I take this 2 by 2 matrix and I multiply it by the coefficients of u and v. Easy enough. This is all just math 6 1. Feels suspicious.
No, can I stop you for 1 quick second?
Yeah, so I'm already running a little bit.
Yeah. No, I just wanted to, as part of the translation, just so that your today's notation is pretty put on ours.
Yeah.
So Justin's dsn is my dn on s.
Oh.
Right? Here's the function. Here's the d letter to say that you're doing the derivative. And this thing is the matrix. In my notation also, there was the point that you were at. There was a little point down here. And then the vector goes in here.
Yeah.
So the notation is kind of different. So I just want to put this on the board so there's a...
Yeah.
Right.
Thank you, Stuart.
Thank you.
It's okay. Ooh, are you okay? Wow, both ends of the cable. That's impressive.
All right. Okay, glad it wasn't on film, or maybe it was.
Yeah.
I didn't have part of that piece.
Yeah, no, of course not. Yeah. I think historically what happened with this stuff, by the way, is that a lot of the people that wrote these early papers had taken undergrad classes in differential geometry, which tend to use these nice old textbooks. And then the newer notation is much sleeker for doing fancier math. And we're slowly starting to see more of this and less of that. Anyway. Oh, now my laptop's not happy. Okay. So now let's do the discrete version of all this, and this is where engineering is going to come to the picture. So let's say that I want to find the curvature on a triangle face, right? Not at a vertex, like inside of the face. Well, it's easy to choose u and v directions. I just choose 2 directions. I don't care what they are. And what am I going to do? Well, conveniently, I have 3 normals on my triangle, the 3 vertices. Right? And although it's a little bit difficult to differentiate the normals in the u and v directions because they don't necessarily align with the edges of my triangle, I can differentiate them along the edges using a similar trick to Topa's algorithm. Right? So what can I do? Well, I could say, okay, I take my second fundamental form, right, and I evaluate it in this, let's see, in the E0 direction, from here to here. Right? Well, it's easy to obtain the coefficients. Remember those C's that I had in the last slide? Just take dot product between E and U and then E and V. And if I do that, well, I should get the curvature evaluated in the U and V directions, which is nothing more than the difference in normals. Right? So I can do that for all 3 edges of a triangle. So what does this give me? This gives me a set of linear equations, right? It says second fundamental form times this 2 vector equals this 2 vector. And this one equals that, this one equals that. Notice that this is a 2 by 2 matrix, but I gave you 3 conditions. This is good, because this is overdetermined. It means things tend to be stable, right? If you've heard about least squares, this is a least squares problem to find that 2 matrix. So we solve it for a triangle. Now in reality, does curvature on a triangle face really make sense? No, so here's the next engineering decision they have to do, which is how do you move these funny second fundamental forms from the faces of my triangle mesh to the vertices. And the way that they decide to do that is they say, okay, well each vertex of my triangle, here's triangle, and he has some normal, and the face has some normal, right? I can take the cross product of these 2 directions, right? This is sort of similar to that discrete elastic curves paper that you guys implemented on your homework, right? What I'm going to do is I'll take the cross product of these 2 directions, which is some mutually orthogonal thing to both of these guys. And I'll take the plane of the triangle and rotate it into the plane of the vertex, defined by this normal, by rotating along this cross product direction, which is sort of the one direction that's in common between these 2. Right? So anyway, what do? I rotate the tangent plane and I kind of drag the that 2 by 2 matrix with it. And now for each face adjacent to a given vertex, right, I now have a different second fundamental form, right? So in general, for example, here I have 1, 2, 3, 4, 5, 6 adjacent faces for this vertex, each of which has its own 2 matrix. Yeah? So what do I do? Well, yet again, I just choose some area weights and I average them all together. So we have 2 sort of stabilizing steps here, whereas the last diagram we talked about had 1. Right? The first was that we solved the least squares problem to find this 2 matrix per face. And then, if that wasn't enough, we multiply a little bit more by averaging all of these adjacent face 2 matrices together. That makes sense? So it turns out that this method is much more stable and indeed enabled the whole literature in rendering to take place after that. So what was our trick here? Well, we wrote down a different formula for curvature. Right? Remember Tobin's algorithm, he defined some matrix and then took his eigenstuff. Instead here, we're going to define some other matrix and then just average them around. And then you can take his eigenstuff, by the way, principle of curvature expressions. And these are just 2 random formulas from differential geometry. Is one inherently better or worse than another? No, but this one happens to yield a more stable scheme for how to compute curvature. And basically, a lot of the early curvature computation papers played this game, where you choose your favorite toehold into theoretical geometry. You write some formula that gets you the curvature from derivatives, and then you discretize it, and you see how well it works. Right? For example, one really cool paper that we won't cover today actually does this in a sort of interesting topological way, where they look at the behavior of functions along the surface and their critical points, and use some of this Morse theoretic machinery almost. Anyway, so going through our list of our favorite geometric approaches that we tend to talk about, right, there's this sort of divided difference trick that we just talked about. And then sort of the other school of thought in differential geometry is this idea of using conserved quantities, right, this discrete differential geometry approach. The idea here is that we want to take structure from theoretical geometry and then adapt it to discrete geometry in a way that it holds exactly. Right? Remember that when I have these schemes like what I was just talking about, there's no guarantee that this 2 matrix has anything to do with curvature. There's just some reasonable way you might approximate it. Here, we're going to say we define the curvature of a triangle mesh to be this, and now we are going to show that our new definition of curvature aligns with our definition of curvature for a smooth surface. See how these philosophies are a little bit different? Cool. And by the way, we're going to, in our explanation of sort of standard citations for this sort of stuff, there's no way to cover this whole literature. I chose one of the standard papers in discrete differential geometry that does this. And it's by some really friendly people in the world. So anyway, remember from I think lecture 1 that we talked about this idea of structure preservation, which is what I just talked about. And it is that we want to keep properties from the continuous abstraction exactly. That we're not going to use just divided differences and hope that things work. We're going to say that the theorem I care about from differential geometry is this, and I want a curvature measure that actually preserves that theorem. Yeah? So here's one theorem, which unfortunately I don't think we covered last lecture. So you'll have to take me on my word, and then we're going to circle back to it later, because I think we will need it again in this course.
This was planned earlier, but it turned out not to be possible to prove without further so you deferred the proof of this thing to later.
Yeah, they say in teaching you kind of have this spiral approach, so this is one that will spiral back to a bunch. But for now, I'm going to kind of tell you that this theorem is true, and you can think intuitively why it might be true, and we'll go back and justify it better later. Cool? So I know this is not too great, but such is life. So anyway, let's say that we have Gaussian curvature. We leave it as just a function along the surface, right? At every point of the surface, it gives you a number. And we have to find how to integrate a function on the surface. In fact, I did that last week, and then Adrian did it again on Monday, and then theoretical end. So you take Gaussian curvature, and you integrate it along the surface. And then you add to that, along the boundary of the surface, that's what this little squiggly D thing is, the geodesic curvature, so sort of the curvature of the curve that defines the boundary. If you integrate these 2 things down together, you get 2 pi times the Euler characteristic of the surface. Right? This is a global theorem, right? Remember what the Euler characteristic is? It's 2 minus 2 times the number of holes. Yeah, we talked about this, I think, 2 weeks ago. So this is a global theorem that tells me if I can measure this local thing about curvature around my toes, right, this little derivative object, and I integrate it all together along the surface, I get a piece of topological information back out, namely something related to the number of holes. Cool? So for now, we're going to take that as our ground truth, and we'll go back and justify it a little better later. Yeah, so we're going to skip right here. So let's say that I have a surface that's built out of polygonal cells. Right? And so in particular, remember that we have this sort of primal dual approach that's going to be very useful in geometry, where we have this primal triangle mesh. And usually we measure curvature at vertices, because otherwise we kind of question as to like, where is this curvature inside of the face, right? So let's say I want to find the curvature at this point here. Well, how can I do that? Well, so let's forget for a minute that our surface is really made out of all these flat faces. And let's say that I took a smooth surface and I kind of chunked them up into these little triangular pieces. Well, if I define this cell V as this sort of Voronoi cell around this point here, then I can say the integral of the curvature here, right, integral of Gauss curvature on the left. Well, so you can look at the topology of the cell as just a disk, right? So now that genus is easy to compute, we just get 2 pi on the right-hand side. And I guess I subtracted the geodesic curvature, which was on the left-hand side, the last slide. Subtracted it, moved it here. And the geodesic curvature actually is intuitive here. Trust me. So the way that we can think about this total geodesic curvature is let's go back to lecture number 3 for CS 468, when we were talking about curves. Remember? And one of the ways that we talked about the curvature of a curve, at least the integrated curvature of a plane curve, hopefully these kind of hefty differential geometry phrases are starting to parse in your head now, is that we looked at the turning angle of this curve. Right? So to get one idea of the total curvature of this curve made out of little linear segments, I'd say I walk along this straight linear segment for a second, and all of a sudden my tangent vector rotates by some angle, and then I keep walking. Right? And that angle of rotation we thought about as the integrated curvature along a segment. Yeah? So if I want to measure the geodesic curvature along this ring here, well, what's one way to do that? Well, all I got to do is add up all the turning angles, which conveniently happen in the interior of these spaces, right? So all these are plane curves, nothing more. And they'll wrap around the bend here just in the easiest way possible. I take 2 adjacent faces and I can kind of unfold them and keep walking.
And that has plane curvature 0?
At plane curvature 0. Yeah, isn't that convenient? So all of the non-trivial curvature computation actually goes back to lecture 3 of this class. We don't need to worry about the surface at all.
Why does this have non-zero curvature? Why does that have 0 curvature?
As zero Gaussian curvature, because it's developable. Yeah, it's just 2 flat pieces.
But the curve, I'm talking about the curve. Why does the curve have?
Oh, remember that it's the geodesic curvature.
There is a turn.
There's a turn along that angle, but it's geodesic curvature. And remember, the way that you're turning is sort of parallel to the way the normal's turning, so everything kind of zeroes out. So anyway, yeah, so just like I talked about, this changes the normal direction, so it doesn't count for geodesic curvature. And this turning angle is nothing more than what we already covered. Ain't that convenient? So something that I was going to add to your last homework, but it already was looking very difficult, so I'll add it to your next one, is to prove that the sum of these turning angles around a cell is the same as the sum of these interior angles around a vertex. Fun fact of the day. This is certainly true, at least if this cell is a Voronoi cell, meaning that this is sort of the locus of points that are closest to this vertex as opposed to any other. This is vaguely intuitive if you squint at it, but not 100% intuitive, so it is worth some proof. But we'll save that for later. Thankfully for us, what does this mean? This means I drew this pretty cell on my triangle mesh, but I never actually have to find these points, right? Because to compute the integral of k dA, what do? Well, I take 2 pi, my favorite constant, and I subtract off the sum of these interior angles here. Right? This is called the angle deficit definition of curvature. Does this make sense? How I've gone? How I figured out how to integrate curvature in this little Voronoi cell? It's actually pretty straightforward in the end, right? And remember that this number on the right-hand side is not curvature. It isn't, right? This number is the integral of curvature on this cell V. In fact, if you don't believe me, let me motivate why this difference is very important. So let's say that I have a triangle mesh that approximates some nice smooth surface. And I refine it, and I refine it, and I refine it, and I refine it, and I refine it. right? What's going to happen as I refine this mesh, right? Remember that here are vertices of my mesh. Here are other vertices of my mesh. And let's say they're really close together, right? So even though they're along some approximation of my surface, right, this vertex and this set of neighbors on a very refined approximation of the surface is going to be basically, they're all going to sit on a plane, right? In fact, the more I refine my surface, the more planar this little itty-bitty neighborhood is going to look, right? This is like calculus 101. Well, what happens here? Well, so the number 2 pi is constant. What happens to this sum of angles all the way on the right? Well, we know that if my shape were actually a polygon, right? So let's say that I'm standing, or rather a polygon on a plane. Let's say that I'm standing at a point, and I draw a bunch of radial angles out, and I sum up all the interior angles just on a plane. This is a circle, and it's 360 degrees. So you get 2 pi minus 2 pi, and this whole number goes to 0. So we've got to be really careful when I measure the curvature of a mesh. This number is integrated over v. If I want an approximation of k, I've got to divide by the area of v. But anyway, this is an easy way to compute curvature, at least Gaussian curvature. And we flip things backward. We say we will define the Gaussian curvature at a vertex of a mesh to be this number that we have just motivated. Notice the game I just played with you. I went through and I started with the theoretical story. I came up with a formula that I can deal with, and now I go back and say I define my curvature to be this. And this is the story that we use a lot. And again, you can divide by the area of v for an estimate of Gaussian curvature. Cool. So remember, this is our Euler characteristic. Take vertices, check the edges, we have faces, and we get this number pi. Yeah? And he depends on the number of holes we have, right? Soccer ball, donut, or this funny double donut thing. And for a triangle mesh, in fact, we have a handy formula that we can get rid of the number of edges because we know each edge is adjacent to 2 faces. Yeah? So how is this going to be useful? Well, what I want to prove to you guys is the Gauss-Bonnet theorem. Remember, I told you the Gauss-Bonnet theorem is really hard to prove when you have to integrate curvature along surface, you got the geodesic term and all this stuff. But I can prove the discrete Gauss-Bonnet in like 5 minutes. Right? So let's say I want to integrate curvature k along my surface M. I'm too short for this projector. And one way I can do that is take my surface and divide it into a bunch of cells, v sub I, and just sum up the integrals over them. Right? All I've done is take my surface, partition it into a bunch of pieces. I can see smiles and nods. You're about to see the game I'm going to play here. Well, we know the integral of curvature in each of these little cells is this formula. Why? Because I told you it was. I defined it to be that. We've got to be really careful in our heads what's a definition and what's a theorem here. Well, and by the way, so this is a sum over vertices I, right? And theta ij will be the jth interior angle at vertex I. Cool? So it's like this angle here, say. Well, so let's move this sum inward, right? So the 2 pi, when you sum that over I, well, that's nothing more than 2 pi times the number of things we're summing over. Right, which is the number of vertices v. And now, what are we going to do? Well, we'll say we sum over all vertices I and all interior angles j, this number theta. Yeah? So one thing I could do is flip my way of thinking about these angles, right? So what did I do? Basically, I iterated over all the vertices of my mesh, and I summed up all of the interior angles next to all of the vertices. So in other words, all I've done is on every single possible interior angle that I can find on this whole triangle mesh, like this one, and this one, and this one, and that one, and that one, and that one. Right? I just add all those angles together. Well, a different way to think about this sum is that I'm going to sum over all the triangle faces of my mesh and add together these 3 interior angles here. And in the next triangle, I'll add together these 3 interior angles, so on. What's the sum of the interior angles of a triangle? This is high school, like 9th grade geometry. 180 degrees. No matter how hard I try, I can't design a planar triangle whose interior vertices whose interior angles do not sum up to 180 degrees. Right? We like radians in this class, so it'll actually be pi. Yeah? So what is this number here? All it is pi times the number of triangles. Yeah? Handy. So what do we do? Well, now we can simplify a little bit, right? We'll factor out this pi, get 2v minus f. Well, we already proved, well, we didn't prove, we discussed, this handy theorem that we have that goes from vertices and edges and faces to the Euler characteristic. So what did I prove to you? I proved to you that under our definition of curvature as this number, at least integrated over a cell, the Gauss-Bonnet theorem holds exactly. Do you think the Gauss-Bonnet theorem is going to hold if I use one of the Tobin's algorithm to compute curvature? Absolutely not. In fact, maybe a fun homework problem I'll have you guys do is actually try this, and you'll find that it doesn't hold at all. But here, no matter how hard you try, even if your mesh is really noisy, this curvature number that you compute is completely consistent. Now, by the way, this curvature locally can still be really noisy, right? It's just a bunch of little interior angles. At least this one property holds. So if this is the property we care about, then we got it. If it's not, then we still got it. So the one sort of final piece of math that I think we need to do today, of course, as usual, we're running low on time, is a way to compute, so this is a way to compute Gaussian curvature, right? But remember, I told you that's not the full story. The full story is that we need Gaussian curvature and mean curvature. So remember from homework 1, right, I gave you a curve and we had this little mini variational argument that said that the curvature direction of the curve, and the way to think about it, is as sort of the gradient of arc length, right? In fact, you guys implemented some little integration scheme that showed you that if you walk along minus the gradient of arc length, eventually you get a straight line, at least if your integration scheme is okay. And yeah, that's one way to think about curvature of a curve. If you read Adrian's supplement for lecture, which unfortunately I don't have too much time to justify, if you extend this to the two-dimensional version of this theorem, what it says is that the mean curvature of your surface along the normal to the surface now instead of the curve is the direction that decreases, or increases the surface area of your surface the most. Great, this is sort of a reasonable extension of this theorem for curves. Although when I use the word reasonable, what I really mean is that we build up about 10 chapters of our geometry book to prove it completely rigorously. But it turns out to be true. Thankfully, if this theorem is difficult to prove for a theoretical surface, it's very easy to use it to define mean curvature for a triangle mesh, because whereas even just writing down the area of a surface is a little bit tricky for a smooth thing, writing down the area of a triangle is something we're very good at. And that's how we're going to spend basically the rest of the lecture today. So let's say that I have a triangle mesh like this dolphin. You have the number of vertices v. Then you can think of the area of this dolphin mesh as a function from that should be R3V, apologies. Well, basically you're going to concatenate together all of the positions of all of the vertices of this mesh, right? Then I'm going to, now that I know all the positions of all the vertices, I can sum together the areas of all the faces of the mesh and get a single number out that's the surface area of this whole guy. Okay, so this is some functional from R3V, apologies, remember x, y, z, to just one number, which is the surface area of the surface that comes out. That makes sense? Cool. So let's study this function a little bit. So I apologize if this derivation is a little hairy. This is the one that I was able to do without the internet on an airplane, and then but probably that means that it can be simplified a little bit. But anyway, let's say that I have a triangle here, and I'm going to choose a convenient coordinate system where I'm going to just pick an arbitrary edge of my triangle, labeling the E direction. We're going to make all these unit vectors. And then we'll say that the other sort of direction that's in the triangle face will be E per. And then the normal of the triangle is N. Cool? I'm going to take a triangle and move it any way I want. So what is the third vertex of this triangle? We'll call it P. Right? And one way to recover the position of a point is to take the dot product, to take its component, rather, in each of the three coordinate directions, which I've done here. Yeah? And what is the area of this triangle? Well, it's nothing more than 1/2 times the base, right? Just the width of the triangle times its height. And what is its height? Well, think about it. So basically, remember that we've written its position in terms of one of the vertices, and we've chosen a really convenient coordinate system. So the height is the square root of the sum of these two squares. No? Does everybody understand this formula? Cool. So let's differentiate this thing, right? Well, so remember we've got to take the derivative in three different directions here. Well, so this is our formula for area. So let's take the easiest derivative first, right? Which is the derivative in the E direction. So notice P sub E does not appear in this formula. So I think we can all agree that this derivative is 0. Right? So now let's take the derivative of the area in the normal direction. Well, what do you get out? Well, if you squint enough, right, you got something to the 1/2, so you'll get that to the -1/2 times 1/2, all this moves around. And this formula comes out. Hopefully you can trust me on that. But what was P sub n for the triangle that I showed you on the previous slide? Well, I drew that triangle. I defined our axes very conveniently, right? So that the first 2 coordinates were the triangle plane, and the third was the normal direction, right? So assuming our triangle starts out on the flat P sub n equals 0 plane, right? Then the first order, the area, the derivative of area in this direction, well, this number is 0, so I get 0 back out. Sadly, it's not that nice for the derivative in this p perp direction. We just get this formula here. Such is life. But what does this tell us? Well, what is the gradient of area with respect to this one vertex at the top of the triangle P? Well, I've told you that 2 of its components are 0, and the third one is parallel to this p perp direction, okay, the p perp. And if you look at it, well, what are we doing here? Well, if we're taking, sorry.
Pn is 0.
I'm sorry?
Pn is 0.
Oh yeah, this number is 0. So then you have this number divided by itself. Yeah, so you get 1, so you get 1/2 b back up. Cute. I know it's missing something. So, I can now add another piece of information to our box, right? We have the position of the point, the area of the triangle, and this really handy expression for the gradient of the area of the triangle with respect to this one point here, right? And all it is 1/2 times base triangle times this vector, E perp. Cool. So now we're going to do a little bit of high school trigonometry. My big goal for this lecture is to do all of this math involving nothing more than 10th grade stuff, which is a little bit tricky. So let's say I draw my triangle here. Here's my point P. And I'm going to define this other point P0, which is a projection of P onto this line downstairs. Right? We're going to start to do some tricky math here. So first of all, what is this height of this triangle? Well, remember that tangent, right, is opposite over adjacent. The tangent of alpha is h over L1. Tangent of beta is h over L2. So we can write down 2 different expressions for h. Right? And let's say that we come up with the number t, which is sort of how far along this edge P0 lives. Right? So let's say that P0 is some combination of R, right, the point on the right, and combination and Q, the point on the left. It slides like this. Do you understand my setup so far? So what is T? Well, it's the ratio of this length to the length of the whole curve downstairs. Yeah? So that's L1 over L1 plus L2. But conveniently for us, I have these 2 expressions for h upstairs that are both equal to each other. Right? So I can substitute in a number for L2 by just dividing by beta. Yeah? So I do that here. All the L1s go away because of the top and bottom, and I get this nice expression there for tangents. So now, we shift our slide like this because we have bigger equations. Remember, we have this point P naught, which is a combination of the right point and the left point, right, with these weights. But now we have an expression for T, so we plug it in, and this is what we get, right, which is that we'll have R times the tangent of this angle here, plus Q times the tangent of this angle here. But remember that our 2 weights have got to sum to 1, so it turns out what we do is we just divide by the sum. And this just comes from plugging in the expression we had in the last slide. So we're good so far, right? Now, I'm completely disregarding times when we divide by 0, by the way, which happens occasionally. This is why this probably isn't quite a proof. But for a cube triangle, it's fine. So now, what can I do? Let's say I define a vector h that points from P0 to P. Notice what I'm doing here, you guys. This isn't just some random set of constructions. Remember that the derivative of the area points in this sort of rise direction, and that's what I'm getting at slowly. Right? So what is h? Well, it's nothing more than the difference between P and this point here. We have an expression for P0 from the previous slide, yeah. So we can plug him in, right? That's this guy down here, and we can plug in P, right? Just subtract the 2, and then pull out some tangents, and this is the expression we get. Right? Notice that P, you get the sum of these 2 tangents here, because it cancels here, and you'll just get P minus P0. Yeah? Everybody with me so far? Stop me if you're not. Cool. Good, because I got 10 minutes. So, finally, I'm going to compute one more number, which is the ratio between the width of this edge and the height of this thing. Right? By the way of doing this derivation, I've no doubt like basically reproved like the law of sines or something, whatever, it's a symbol involved. Yeah, so what is this ratio? Well, now we have everything we need. We use our favorite substitution upstairs, right? Same one we used before. On the bottom, right? Well, what is the what is the height of this triangle? Well, again, you think of it as L1 times tangent alpha, right? So we get this number for the ratio. So finally, we can combine all the elements that we want to get the gradient of area, right? Because remember, what is the gradient of area? Well, it's this length times this unit direction, right? So remember, I had an expression for h that I computed before, and I'm going to multiply him by the ratio of this length, which is what we really wanted, divided by the ratio of the length I accidentally got by subtracting these 2 points. Cool? We had all these expressions that we had before. We just plug them in, and we had tangents that we moved to the denominator, so we're going to get cotangents back out. And what we get is this really handy formula in the end, right? Which is that we can get the gradient of the area of this triangle by measuring the cotangent of these 2 angles, alpha and beta, and then just multiplying them by vectors along the edges, right? So P minus R is just this vector, right? So it's that vector times the cotangent of the angle opposite him, plus this vector times the cotangent of the angle opposite him. Yeah? So I know this derivation is probably the world's hairiest derivation of this cotangent formula, but the nice thing is that every single step just applies like, you know, rags over run, which is kind of handy. So anyway, this cotangent formula is humongously important, and we're going to see it repeatedly in this class. This is the first time, and we'll come back next week, and the week after, and I believe the week after that, all seeing it in different contexts, which is kind of fun. Actually, I lied. Next week we talk about geodesics. That doesn't matter. 2 weeks ago. So anyway, remember that we really want the gradient of the area of the mesh, and not an area of the triangle. So all we do, right, the area of the mesh is just the sum of the areas of its triangles. So to get the derivative of area with respect to the position of point P, we're going to sum this guy up over all of these things. Right? So remember what that is. That's cotangent of this angle times this vector, plus cotangent of that angle times the same vector. Right? So in other words, we're going to iterate over all the neighbors of a given vertex P. Right? And we're going to say P minus neighbor J, right? That's this difference here. And we get these 2 different cotangents that are both sort of adjacent to this edge, right here and here. And we're just going to sum all those up as we walk around the loop. And this gives us our gradient of area, right? So even if our derivation is a little hairy, in the end, the gradient of surface area is this very easy thing to compute, right? You just compute all these interior angles, which we needed for curvature anyway, for Gaussian curvature rather. And now we combine them in another way, and we get the derivative of surface area to the surface, whose norm, right, by how I justified before, is nothing more than the mean curvature, right? So life is good. By the way, you should notice that as we refine the mesh, all these things become planar, and yet again, this thing still vanishes, and you should check that out. Right? So this is still sort of an integrated thing. Actually, is this true? I'm not sure. I'll make a post about this. I'm not sure if this is point-wise or not. But anyway, what do? We define the mean curvature. Yes, it is true. And we because these derivatives go to 0. Sorry. Or these differences, right? As points get close, differences get small. It's a rough. Anyway. So the integrated mean curvature normal of the surface is nothing more than we define it to be, right, this thing that I just derived for you in excruciating detail. Right? And now we have a completely consistent choice of mean and Gauss curvature. Right? The Gauss curvature preserves this nice topological theorem. The mean curvature preserves this nice fact we have about surface areas. Right? And just like we can go forward from principal curvatures to Gaussian mean curvatures, we can we can go backward and sort of invert that formula to get the principal curvatures we want. Cool? So this is like a completely different approach from Simon's paper that uses this nice least squares thing. Is it more or less stable than the least squares paper? I would argue it's probably less stable, right? You're computing all these little interior angles, and they have no knowledge of anything farther away in the mesh, nothing. But it's consistent. And for a lot of, especially simulation applications, sort of preserving these things exactly can give you a big win for certain things. So what do we do? Our pipeline is we compute these integrated Gaussian mean curvature. Once again, if you want pointwise, you just divide by the area of the cell. I don't know why that's homework. It's not homework. There are different ways to compute areas of cells, and we will no doubt talk about this a lot in about 2 weeks when we introduce the reflection. And if you want the principal directions instead of just the curvature values, well, the paper itself actually basically ends up using Tobin's method to get the principal directions back out. A little bit disappointing because it doesn't use any nice differential geometry. So I've defined for you now 3 different ways to compute curvature, and these are by no means the only ways. And I'll just mention a few other ones, and then we'll be done for the day. Another way to think about curvature is we say, okay, well, the triangle mesh is a little bit annoying, but at the very least, there's one place that we can measure. So there's sort of 2 places, rather, that we can measure areas, or angles, right? First one we already talked about, which is the interior angles next to a vertex. The other is that each of these edges has sort of a folding angle, right? So let's say that we think in the back of our head as an edge is actually a slightly little, we add like a little, there's some engineering word for this, when you put in a little smooth pipe on a sharp edge, like a filling, yeah. I put in a little filling that's circular on each of the triangle edges, right? And, and I look at the bending angle of my edge. We'll call that beta. Yeah? This is the angle between the 2 faces. Notice all these things are very easy to compute on a mesh. So if we make our little filling with a circle here, right, then no matter what the radius of the circle is, if you look at the angle that the filling makes, it's always the same angle beta. Right? That is, if I have flat piece, and circular filling, and I draw little lines that go out to the beginning and end of the circular filling, I'll always get the same angle beta back up, no matter how small the filling is. Well, this is a nice property to have. Remember, in discrete differential geometry, we really like properties that hold at every scale, not just in the limit. Right? And here's one. Again, remember our strategy. We get one little toehold into math, and then we're just going to exploit it as much as we can. So here's our toehold. Right? Here's our preserved structure. And what are we going to do? Well, we'll say that the integral of the mean curvature along our filling is pretty easy. Right? Because a circle has constant curvature. Right? That's something that we discussed in class. And the integral in this direction is easy because it's just constant. Right? So the length of the edge times the superior angle divided by 2. Yeah? So one thing we might do would be to use this dihedral angle, this angle between the adjacent faces, to derive a curvature value. And in fact, people use this for applications where you have a triangle mesh and now you want to change the triangles, right? So this is a very common operation that you do on triangle meshes, where let's say that I have 2 adjacent triangles, and for some reason I decide that, in fact, I might want to get rid of this edge. So here's the same triangles again, and flip it, right? And you can see, for example, in this case, flipping this edge is probably a bad operation because I took 2 sort of nice, almost equilateral triangles and made them into 2 obtuse triangles, right? But in the reverse direction, my mesh might have gotten a little bit better, at least for certain simulation applications. So what do these guys do? They say, well, I'm going to flip an edge when it makes lower curvature for the surface, and now I have a measure of curvature that's based on edges, right? So for their application, this measure of curvature makes a lot of sense. Again, engineering, not math. We define some number that has something to do with curvature and happens to be tailored to the application we care about, and then we exploit it. I always get signs wrong.
Well, when you look at that, it looks like you have the anti-GIJ for the dash line.
Yeah. Oh, in this particular case, you mean?
Yeah.
Yeah, it does invert the sign, and I don't know this paper too well, but I think they don't care as long as it's small. Because oftentimes the way that you triangulated the surface initially was a little bit arbitrary anyway. So who's to say that this one's not better? Is that a good explanation? So we should look closer at it. There are other methods that we won't have time to discuss. For example, maybe what you care about is sort of a simulation or a fairing approach, and what you really want is to make sure that your curvatures are smooth functions. So this paper actually compares their curvatures, which get these very noisy little, isolines. They compare it with their isolines, very smooth little curves. And it's yet another differential geometry approach. In fact, maybe what you want to do is think about this in image processing language. Remember, image processing is all about blurring stuff out. Right? We defined like 1,000 different blur operators, and then we apply them in our favorite ways to take a photograph and make it something nicer. So these guys do something similar, where they take some of our favorite localized estimates of curvature, and then they just blur them out. And that way, your curvature is this very stable function along the surface, and it's very useful for doing rendering applications, where again, we care more about stability than accuracy. In fact, they're able to get robust estimation. They're able to get not only stable numbers, but accurate ones, by saying that, really, I only want to combine my curvatures with other points' curvatures when those points sort of geometrically look similar. Right? So in this sort of pencil-looking model, right, there's this very sharp edge that happens. If I just blur the curvature blindly along the sky, like I use these weights in this circle here, then what's going to happen is I'm going to accidentally combine these guys' curvatures with my happy flat curvatures up here and get some weird halfway number. But perhaps I can detect this sharp feature here and only blur things to the left. Right? This gives us a much more robust version of curvature, right, where they use weights that are just based on sort of nearby guys, that makes sense, than just blindly convolving with your favorite Gaussian. Right? This is, if you're taking an image processing class and you've seen the bilateral filter, this is precisely what's going on in this paper along the mesh with certain weights. And there's tons of other approaches. For example, one thing you could do that I didn't talk about would be maybe you've learned about B-splines and quadratic surfaces, and maybe I take a little neighborhood on a mesh and I just fit one of those in some least square sense and use his curvature. That's another reasonable approach. Maybe I use some other formula, some function of curvature, where you evaluate it, you got to figure out, make sure if your function converges. And finally, one really bizarre approach that I kind of like is that you use your favorite really complicated curvature computation method that takes hours, and you do this on like 25 meshes. You just do a bunch of examples, and now I'm going to throw like SVM or some learning technique to learn the function from vertex positions to curvature, and I don't care how I got there because it's still stable. Right? Each of these is tuned for a different application and has a different thing in mind. So what you really should do is, if you need a method for computing curvature on a mesh, as many of us do, I use it on a daily basis, you should just try them all until you get one you want and then stop trying. And then when it stops working for you, try some more. Because there's so many different papers, and chances are for 98% of applications, it won't matter which one you choose. But for that 2%, you're going to have to do a lot of special tuning. So anyway, we'll stop here for today. I think my office hours start now. I will be out of town on Monday, so this is your last chance before Wednesday if you want to ask about coding stuff. But I think we're done for now.
Let's say there's solution sets on the back table.
Oh, cool.